Hi, my name is Moshe Shadmon, and I'm the founder and CTO of ScaleDB. And I'll try to explain and discuss what is special and what we do and what is special in our product. So ScaleDB builds a storage engine for MySQL. And there are two special features about this storage engine. The first one, we use a shared disk clustering architecture, which means that you could scale by simply adding nodes to a cluster, and all the nodes share the same physical data. The second unique feature that we have is a unique indexing technology. And I'll try to go over those two main features and try to explain what we do and how we do that. So just a quick overview on the ScaleDB Storage Engine. So it's a storage engine for MySQL. The main features are shared disk architecture. It uses what we call a multi-table index, and I'll discuss that. It's a transactional storage engine. We support row-level locking. It's ACID compliant, and it's disk-based storage engine, which means the intention is to scale in a way that we can support the largest data sets. We don't assume that data or indexes needs to be in memory in order to operate efficiently over the data. So the first topic that I'll talk is about our shared disk architecture. And when I talk about those on this topic, the thing to look at and try to consider is the manageability of the system, the availability, the fault tolerance, how scalable we are, the performance, obviously. And we need to see how all of those, and obviously all of those, affect the cost of ownership of the database that we maintain. So the first question that comes up when you say a shared everything or a shared disk solution is, what is the difference between a shared nothing and a shared disk or shared everything solution? So let's go briefly over the main concept of shared nothing, see what the limitations are, and how we deal with those things in a shared disk environment. So with the shared nothing, we start from a database, and we create our tables on this database. And at some point, the database grows to a size that it's not scalable anymore, either because our data sets grow beyond a certain size, or the number of users that exercise the database is too large. And so we say, okay, let's try to deal with this thing, and the way that we deal with it is we partition the data. So there are different ways to partition the data. A simple one would say, let's just take different tables and put different tables on different machines. Once we do that, it seems like it would be easier to scale because my data is now spread across multiple machines, and so are the users. But this is not that simple. As all of us probably know, it's the question on how to partition the data is complicated. So, for example, table B could be very large, and tables A and C could be very small. So partitioning by just simply placing different tables on different instances could be complicated. And from the other hand, when we partition, we want also to partition in a way that the usage of the users would be equally distributed across the different servers in the cluster. And again, this also raises some complications and difficulties. So it's very hard to predict the usage patterns that would tell us how to partition the data. It's hard to avoid data skews. I mean, another problem that exists, even if I partition my data, I very frequently have to ship data from one node to another, because my query might go to table A, but I need to join data which resides in table B, and now I have the issue of how do I get the data from node B and bring it there. So all of those are things which limit our partitioning. There is another approach to partition, which is partition breaks one table into different components and places each part of the table on each node of the cluster. In this example, we've partitioned by salary, and obviously queries that query data for a particular salary could go and be satisfied at the correct node. However, queries that are based on another column or queries, range queries, are very difficult to satisfy using this type of model. So I would say if you could partition your data efficiently, in the sense that the data is equally spread over the database, and you could partition it also in a way that the user activities are evenly distributed between the different servers, then you could work well. But this is very hard to do, and usually those are things that even if you are able to create a scenario like that, my database evolve and change over time. User patterns and user queries change over time, so it really becomes a moving target. So we've got here examples of query by salary, which would be satisfied efficiently if we break by salary. However, there are many examples where this model wouldn't work. So what is the alternative? So the alternative that we took is called a shared disk approach, where when our database grows, instead of partitioning the data, we're able to set up a cluster of servers, whereas each server is able to access all the data. All the data is available to all the nodes in the cluster, and if you take this approach, there is no need to partition the data. So let's look again at those types of problems from a different aspect and see the differences. So with the shared nothing, I have my different nodes, and I've partitioned the data somehow, and then I need to direct my calls, my users, to the box that potentially can satisfy their queries. And then those boxes have to talk to each other, since in many cases it's very hard to complete the query on a particular box. But the problem, that raises question. For example, if one of the of my servers fails, what do I do? So I need to do some kind of replica of the data or some kind of mirroring, and obviously now I'm also in the process of synchronizing between my server and my master and the slave. If I do that and one of the servers fails, I can obviously direct the calls into the slave, and then I have to now communicate between the available boxes in order to be able to show a complete solution that is able to retrieve all the data that is needed to satisfy the queries. However, even with this model, and even if we were able to replicate the data, if the number of users suddenly grows and the users' patterns are not evenly distributed, it's very complicated to scale this model. And even if the calls of the users are evenly distributed, I'm limited by the number of servers that I had in mind originally. And if I need to scale that, I have no other alternative other than put the system down and repartition my data such that the distributions of the users and the data would be better. With shared disk approach, those problems are eliminated. And the reason is that if one of the nodes fails, then nothing happens. All the other nodes can satisfy all the queries, and all I need to do is redirect the calls from the server that failed to the surviving servers. if I want to scale my system, all I need to do is add additional nodes to my cluster, and since all the data is shared, any one of those nodes can immediately accept calls from users and satisfy their queries. And in addition, if my data sets grows, I can add additional storage to my cluster, which is again accessible to all the nodes. So this model that we present here is one of the technologies which we have implemented in ScaleDB, and it offers a new way to scale your system and deal with your data, which is different than the alternatives that people were using today with a shared nothing approach. So I'll jump from here to a different technology that we've implemented that deals with the indexing, which again is different than the way that indexes have been treated or have been used until today in MySQL and in conventional other databases. So let me skip that. And if somebody is interested in more details, we'll show a demo. I have later today a presentation downstairs. Yes?
Is the ScaleDB Storage Engine proprietary or?
Yes.
Oh, okay.
I take it you support things that looks like a picture of a NetApp there. You support, I take it you support like other shared disk arrays, or is it always NetApp or NFS?
Right. We don't care. I mean, you could start from a simple solution and then go all the way up to.
But if it uses a shared file system.
We can use any type of shared file system, NFS or NAS or SUN, whatever.
Do you operate on the file system itself, or do you operate on a block? Do you need a file system?
We need a file system. We operate on a block. So the second technology that we've implemented is an indexing technology. We call it a multi-table indexing. So all the databases, whether they're commercial databases or open source databases, using B-tree as their main structure. And the thing with B-tree is that it's a structure that allows you to efficiently access data. But that's what it does, and not more than that. And our structure, we use a different indexing scheme that addresses not only the data, but also the relationships between the data. So I'll try to explain and give you more detailed understanding on how we do it. But the bottom line is that this indexing scheme is faster. It gives you better performance, and I'll try to show you why. It has a very small footprint, and it also, because we maintain the relationships between the data items in the index structure, it helps you to maintain the referential integrity with a very small overhead. Actually, there is an overhead to maintain the referential integrity with our approach. So let's take an example where we have college information and we want to join enrollment information with student information with the college information. So I have my query here, and there are a few ways to satisfy, in terms of the engine, a few ways to satisfy a query like that. So the first way, I've got my three tables, so I can go to my enrollment information, pull up the row from there, and then join it with the student information and the college information. So that would be the conventional way to do a join operation. The second way is to build a materialized view. Now, MySQL doesn't support materialized views, but with commercial databases, it's doable, where you create a new table which includes the aggregates of the source tables, and it's optimized to satisfy your query. If you were able to build this table, then your queries would be very fast. I can go directly to the row that contains all the data, and I don't have to go to the source table. The problem with this approach is that we obviously need to create a new table, the materialized table. And not only that, we have to synchronize this new table with the source table. So if I change a student address and it appears in the materialized view table, then I have to go there and make the change there as well. So even when it's doable to use those tables, people have used it very, very carefully and in very few cases, and there was always the consideration between the synchronization and the maintenance of this table and the performance that you would be able to get with or without this table. So we present a different approach. Our index structure maps not only the data, but also the relationship. So we don't create this extra table. We don't create a structure that needs to be updated or maintained. We keep the source tables as they are. And then when there is a query, we're able to satisfy the query with one index lookup that would end with pointers to the three source tables. Once we are there at the end of the index lookup, we pull up the data from the source tables and assemble the result set as if a materialized view was there and ship it to MySQL. So MySQL is operating thinking that a materialized view exists, whereas it does not exist. And the engine allows, the engine collects the different rows that needs to assemble the view on the fly and returns them to MySQL. So I'll show you how this is done in a little bit more details. So how do we build those views, or how do we maintain the information of a need from a view for a view? We do that by looking at the primary key, foreign key definition. So if you created your tables where you describe relationships between parent table and child table, we look at those definitions. So in this example, we created a department table with a foreign key to the college table, so we know about this relationship. We create the course table with a foreign key to the department, so we know about this relationship, and so on. So we capture those relationships, and then there are two things that we do, or two rules that we operate with. The first one, we let MySQL know about those new tables. So we let MySQL know that there is a new table which would be for department and college, and another table which would be course, department, and college, and so on. So we build those tables for MySQL. So MySQL is now aware of those additional tables. The second rule that we have, we don't maintain physically those tables. So we see here the additional tables that are informed to MySQL. We see that the physical table, or the table which are maintained by the storage engine, are not changed, and we see on the right side there the tables that MySQL is aware of. So MySQL is aware of 9 tables, and there are physically stored only 5 tables. So the next step, we look at, we are taking a query that needs to join information from different tables, and we're able to say, instead of exercising this query by doing join operation, going to one table, pulling up some data, going to another table, pull up some data, what we do, we say, look, there is a new table, which is the view table, and instead of sending this query, send the query which would simply go to the particular row in this new table that we generated and pull the data from there. And if you were to use this method, instead of doing 3 index lookups, the search would end with a single index lookup that would pull up the data, assemble the new row from the materialized view table to MySQL without maintaining such table. So I'm told that I don't have any more time, but there are two things. I mean, one is if you want to see more details in the demo, I'll show it later. I think it's 425. And we have also a booth downstairs. And we are going into beta, so if you are someone who's interested to be a beta customer and try the shared disk, the clustering, or this indexing approach, we are very interested to talk to you. So thank you very much.